Okay, perhaps we can begin.
Yeah, I guess we are live. Sure.
Yes. So welcome everybody to this week's Majorana-Raychaudhuri seminar series. We are very happy to have Hamsa Padmanabhan from University Geneva, and she's going to talk about insights from data-driven techniques from the distant cosmos to prehistoric Earth. Maybe I'll send you a reminder when 5 minutes are left.
Sure. So I'm going to tell you, like the name suggests, on a lot of interdisciplinary topics, some of which I did when I was at Geneva and also now with paleontology and geophysics, which you can see as the prehistoric Earth. And this is all coming together under an umbrella of data-driven techniques because data is becoming so important right now and there is so much of it. And one thing which we have realized is that there are a lot of, synergies between various different aspects, not just astrophysics, cosmology, but also geophysics and paleontology, by using similar techniques by which we can extract the maximum out of the data. So I will try to give examples of this and how it all fits together using these examples. So we'll just, as a name, as we just said, like we'll just have a landscape because I think over here most of the audience is very theoretical. So we can go and ask about the introduction of the topic, like what exactly is the whole thing all about, and then the scales and all which are useful. And then I'll describe a couple of problems in cosmology and astrophysics, which is to do with data driven science, like basically the tracer to halo mass relation, one of the things which is very important to understand several outstanding problems in cosmology, and also how that works in a different context, like you use the same kind of approach from data to understand the earliest black hole. So we can also do that, and I'll give some examples. And then coming to a very interesting part, which is actually coming down to our Earth and its paleoclimate, like basically on its temperature evolution, what kind of data there exists, and how you can basically use something called inversion theory to understand better. And I'll conclude with some future outlook. So just to set the scale, I think this must be familiar to the most of the people, but just to realize that we have a lot of insights from right from the microphysics regime up to the, what we would call the cosmology, astrophysics, which is here. And I think people are all familiar that essentially when we do cosmology, we are looking at huge numbers over here, like 10 to the 12, 10 to the 16, 10 to the 22. Whereas in the micro regime, quantum mechanical and those kind of regimes, we are really looking at 10 to the minus, like angstroms and things like that. And what is quite important for a cosmologist, that if you are a cosmologist, then for you, how atoms are to a condensed matter physicist, galaxies are to an astrophysicist. So they are like the building blocks and they are like the units. And the scale at which galaxies are is something like about what we would call between galaxies a megaparsec or a million light years. And this is the number which we are all going to be thinking about when we do that. And what is quite interesting also, again, from the point of this talk, is that between these two sits nicely the Earth. The radius of the Earth is somewhere, in between the very, very, very large scales, which is like astro, and very small scales, which you would do in your in theoretical physics. So the first part, which we would like to understand, is about cosmology. And something very interesting in that is the hydrogen. The reason is that hydrogen is the most abundant element in our universe. And there is a technique by which you can map hydrogen across a large volume interval. And you can basically try to map hydrogen across the universe. So this is something which is very well done using what is known as halo modeling technique. And I will try to describe some of that. And the main thing to understand here introductorily is that when you look at the composition of the universe, we know that it has a very strange one, no doubt. We have dark matter, dark energy, which we don't understand. And as everybody knows, this pie chart, Baryons here just refers to normal atoms, and as we know that that's a really small part of the total matter energy content. What many people may not be so familiar as this figure is this figure, and this right hand side figure just says that this baryons, or the atoms itself, are also a little strange in the sense that the kind of things which we understand as atoms, which means stars and things like that, planets, all the collapsed things, they are just less than 10% of the total. So the rest of the substance is basically gas in different forms, different phases. You'll find different kinds of notation, but basically it is gas. And not just that, basically it is hydrogen. So by volume, you have this as hydrogen. The entire universe is in hydrogen. We can do a very good approximation. And this is something which we would like to, make use of when we look at when we look at cosmology, and we would like to sort of map this hydrogen across the universe. So when we want to do that, then we actually use a very interesting feature. I think most of the people are aware that the hydrogen emits in this characteristic 21 centimeter. 21 centimeter is just the spin flip transition between these two states. And this particular transition has a frequency of 1420 megahertz, and it is lying in the radio frequency regime of the electromagnetic spectrum. Though it is a very strongly forbidden transition, it is useful in astrophysics and cosmology because a huge amount of the universe is indeed in hydrogen. And that is why, just because of the numbers, you can see, for example, our own galaxy, that this neutral hydrogen, you can map it, and you may say different parts of it are different densities of hydrogen, neutral hydrogen, etc. And you can do this for other galaxies too. And what is now becoming interesting is you can do this for the whole universe. So this is just an animation. I hope it will play. Yes, it is playing. So you can go up to a large number of galaxies. Let's say you go to a galaxy very far away, and it also has a lot of hydrogen. What happens in this technique is this hydrogen, we know, is emitting at the 21 centimeter due to these gas emissions. And this wavelength is becoming stretched. We know that because of the universe expanding, and you have the wavelength going to redshifted wavelengths. And because of which, at a telescope on the Earth, you can make a map in this 21 centimeter, but of course a redshifted version of 21 centimeter. So depending on where that particular surface is, you will get a map in a certain color. You can actually call it color, right? Because it's a certain frequency. And at a lower something nearer will get you a different map, and so on and so forth, where you can make a three-dimensional picture really of the evolving universe. So that is really powerful. And as you can see, this is why this particular technique is extremely having great potential. So the main thing about it is that you can calculate that between today's surveys, like we have galaxies, which are pinpointed surveys, deep surveys, those have gone quite low. Of course, with James Webb, we are doing better. But again, they are pencil beam, just like point particle surveys. And these are what astrophysicists study. Whereas cosmic microwave background, which is right up there, is something that the cosmologists study. So between the two, it is very interesting that you have this big amount of line intensity mapping to map out the universe in hydrogen and maybe in other molecules and atoms as well. One thing we can take away from this figure is that if you look at this galaxy survey, you see that if you compute like the amount of volume which you will access, it's roughly about 1% of what you can actually access up to your horizon. Whereas if you take the intensity map, you may go at least about 2 orders of magnitude more, almost 2 orders. And that is why it is a very important gap which is bridged by this intensity mapping. For example, to do this in practice, you can use all the data. This is what we do in some of the papers, and I'll say a little bit about it. Take all the data and importantly, have a model which kind of brings them together with calculations. And that is what you would like to use to predict what next generation telescopes will be able to do with respect to intensity mapping. So that is really what is called a halo model. This slide is slightly technical in that respect, but we will just look at the main points without going into details. The signal in an intensity map is usually given in terms of what is called a power spectrum. So a line at a scale at a redshift, it's power. And what this power spectrum is made up of is the underlying dark matter. So CDM is dark matter. There could be other theories of dark matter, but basically for now, we'll just keep this. And on that, you'll have other things, and these things are astrophysics, essentially. So these both together are what makes your signal. There is another component which is something to do with small scales, which has something to do with the Fourier transform of the way the gas is distributed. No, we don't have to worry too much about that. But main thing to keep in mind is, if you want to model this quantity, which is the astrophysics, which is going inside your signal, you need to connect the astrophysical part to the dark matter. So this is called a tracer to halo mass relation, and that is really like a holy grail where you want to get that. This could be the mass of hydrogen, this could be the luminosity of certain emitting things, but when you connect it to the dark matter halo, then you can really derive the main quantity, which is interesting in intensity mapping. And how do we do that? For neutral hydrogen, we did this in an early series of papers. And this was like the form which is coming out of many of the analysis. And what really was very interesting and a pleasant surprise was, even though these quantities are astrophysical, a set of dominant parameters could be found from the data. By what do I mean by data? I mean all of the data which exists till now, not the data which is going to come. But even with that, there are very tight constraints you can place on the model parameters, which describes the astrophysics of neutral hydrogen. And what is very interesting is, again, this is just a bird's eye view, that when you do things like this, then you can go to other things, like you can go to carbon monoxide, which is also very interesting for intensity mapping. You can go to other regimes, you can go to galaxies, and you can actually make something comprehensive out of it, where you connect whatever you see, which is like the baryons, when by baryons, of course, here I mean atoms, to the dark matter halos, all the atoms. And from that comes a lot of very interesting outcomes that you can actually find out from all the astrophysics, which is, what are the principal components, if you like, what are the dominant variables, and what do each of them do. Also, what is interesting is you can potentially use this to go ahead to do more theoretical things, or synergize with simulations. So let me just summarize this part by saying that if you go towards a kind of halo model framework, or you go to data-driven framework, you are able to calculate things very fast, because you have just filtered your data into principal, components in some sense, into dominant components. And not only that, you include many models easily, and you also know each of the parameters, what is its today's value, by which you mean priors. And very interestingly, for theoretical studies, if you don't do that, for example, in hydrogen or any other, astrophysical data modeling, something which is astrophysical might show up in cosmology, and then you would not know that it is actually an astrophysics effect, and you underestimate the error bars, and it might lead to various dangerous things, like, for example, new physics. So that is why it's quite important. And the last thing is that when you have these very small scales and you have simulations, which are very detailed things, which are done at microscopic levels, then you find that if you can match that to these kind of dominant features, you will be able to ask questions like, what physics is captured by each of these parameters? And that just bridges the gap between physics and the data. So these are kind of summarized in some of these articles. This is a book chapter and a review article. And the one here is actually something to do with this first part, because this is on a particular experiment. There are so many hydrogen experiments. One of them, a salient one, is square kilometer array. And this is on how we can basically look at cosmic dawn and reionization, which is a chapter we co-led for that. So that is really the thing we want to do here, to take the data and to go into its dominant characteristic. But there is more, that you don't want to just stick to hydrogen. You want to go to other regimes, like you want to look at other molecules, atoms, etc. And the reason for that is that I told you that you do this intensity map where you take a telescope and you look at hydrogen across a large amount of the universe. But on the ground, doing that is not very easy. There is a lot of material between this signal, which is cosmological hydrogen, and your telescope. And all of that is collectively known as a foreground. Foreground could be things emitted by our galaxy. There could be a lot of extragalactic point sources, various things like that. And together, this foreground makes up about 100,000 times brighter signal than the cosmological one. And that's why, if you want to really do at least the first few studies with this intensity mapping, you have to bring in more kinds of elements, substances, and do what is called cross correlation. So cross correlation basically is interesting because, let's say you have one telescope and it measures a signal with some noise. Most likely, if you have just that signal correlated with itself, your noise will stay back. However, if you look at this, we don't have to go into much detail. It's just a bird's eye view, basically, that if you look at this and you look at another telescope which is doing a different regime, then what happens is that most likely these two noises will not correlate. So you will actually end up with just the signal. And that is one way to mitigate systematics. And there are some details about it. But the main point is that if you have hydrogen and some other survey, cross-correlating it may be a good idea. One thing which it is useful to cross-correlate is carbon monoxide. So carbon monoxide is a molecule which has a ladder of states. So that is very interesting because it has this 1-0 transition and 2-1 transition, where 1, 0, etc. are these J quantum numbers. So you have a ladder when carbon monoxide emits, which is always equispaced. Like, for example, the lowest transition is 110 gigahertz. The next transition, 230 gigahertz, like that. And why it is important is that this is the same kind of effect which is there in redshift. So as you go down in redshift, also the numbers become linear multiples of each other. So if you make a band, which is what we have done, this is basically one of the project called COMAP, which I and many others are involved in, Carbon Monoxide Mapping Array Project. It is led out of Caltech. It has this telescope, which has a frequency band, which is centered somewhere here. And what it does is that in that band will fall different kinds of carbon monoxide transitions from different frequencies. And that is why it is from different original frequencies at different redshifts. So why it is important is because if you take this and you cross-correlate it with a simpler or a little bit lower band, then you can isolate a signal coming from a high frequency just by using the power of the ladder. So carbon monoxide is very interesting, and its correlation also will be interesting. And one of the ways in which you can do that is, first way, there is an early science, which is one of the papers did discuss about it. It was about 3-4 years ago. And one thing which was this experimented is it was the first one before non-21 centimeter to reach an early science. And whoever is interested could take a look at this focus issue, which actually showed all the papers. And what is important for us is that bringing together again this data with the other data, like for example, carbon monoxide, will be very important for astrophysics. Here I'm showing just one of the graphs where if you take galaxies and if you take this 21 centimeter, you get better constraints. Like for example, you don't have to pay attention to the numbers here, but what is the main point is that if you have, for example, a constraint with and without a prior, if you have the prior, it almost brings you back about 50% or 75% better than if you did not do the cross correlation. So this is done with one of the 21 centimeter and one of the galaxy survey, but this kind of thing holds for almost all the things, including carbon dioxide and carbon monoxide and various other things. So basically, this can be used for many things. And here I'll just give you two small examples of what this cross correlation as well as the parameterization can do. So we had this 21 centimeter with just the vanilla lambda CDM, cosmology, and so on. But if you want to do something different, like for example, inflationary scenarios, as we know, we have an FNL parameter, a primordial non-Gaussianity. And that primordial non-Gaussianity you can put inside your halo model. And when you do that, you can ask what constraint comes on this parameter due to the data which is there in hydrogen. And like that, we can do many other things like early universe as well as dark matter. So dark matter is also something which those 23% which we don't understand. For example, if you had this candidate known as axions, this is work done by a student, led by a student with us sometime about 5 years back. What is interesting is that if you have this particle, then it will change the power spectrum of the dark matter. And given that the total hydrogen, we have constraints as well as on the power spectrum, we can use the fact that the mass changes the power in order to set constraints from the 21 centimeter signal on the mass range and abundance range of such candidates. So that is quite promising. And you can do this for other theoretical studies as well by putting it into the picture of the halo model. So that is basically what we can do about the cross correlations and about like the 21 centimeter. Now we will just check why this is also quite interesting for other probes. So by other probes, you can look at, for example, multi-messenger probes. By multi-messenger, most of the time, we mean also the gravitational waves. So not just like the electromagnetic spectrum, also the gravitational waves. And here we have now new data, firstly with James Webb Space Telescope on black holes, and with pulsar timing arrays, as we all know, the nanograv data on the mergers of the supermassive black holes. So when we look at that topic, we first realize that if you take James Webb Space Telescope observations, there are many very interesting parts to that to it. Now it has been running almost for 3 years. And along with all the things it has found, one of the very interesting things it has found is extremely massive black holes. So the black hole masses can be estimated with the help of some spectral lines and so on. And what the James Webb Space Telescope has discovered are black holes at very high redshifts. So you can see, like, this is one of the graphs, redshifts greater than 7, like this, also around 10, similar to that. And what they find is that these black holes are overmassive. So overmassive simply means that in the local universe, we have mapped the black hole mass to stellar mass. So again, just to orient you, this is a log scale, this is a log scale. And the stellar mass is just the mass of all the stars in the galaxy. And it is measured in solar masses. So for example, here will be 10 to the power 9.5, 10 to the power 10, like that, in solar masses. And black hole mass is similarly oriented. And if you look at the black hole to stellar mass in the local universe, it is somewhere here. But the black holes being discovered now at the high redshifts are really much bigger, maybe by a factor of 1 to 2 higher than here. Very interestingly, there is one black hole which made it to the press and was quite talked about, because its black hole mass and its stellar mass, the galaxy's mass, were almost equal, which is like 1,000 times more than what you expect from the local relation. The main problem with the fact that this is happening is that how did such big black holes form? And that's what actually caught a lot of news attention and so on, because this is a long-standing problem, right? So this is a problem because early black holes have been indicated to be 10 to the power 9 to 10 to the power 10 solar masses, and they have been forming, as far as we can see from their positions, from their locations, about a few million years after the first stars. And this is a little puzzle, because you need, in any of the reasonable models, at least a lot more time to have continuous accretion to grow such black holes. And that's why these two things are a little bit, out of phase, because you can't really reconcile this with the short lifetimes. So basically, when you look at it again from the point of view of data, as I said, the tracer to halo mass, you can ask, okay, you have black hole masses, you have the dark matter halo. What is the relation between the two? So very interestingly, you can show this relation like a comparison. So for example, if you had the galaxy stellar mass, which was what was plotted in that graph, and you had its dark matter halo mass, it runs like this. This is constrained from a lot of data. And this is, again, a data-driven graph over here. What you see is that the stellar mass evolves quite little with respect to the dark matter halo mass, and all the way from local universe to very high redshifts. But this is not what happens to the black hole mass. If you take the black hole mass and the dark matter halo mass, which by the way can be constructed from theory, from weak lensing, there are many ways, you will find that it grows very high. Like it from local to the high redshift, it goes by through 3 orders of magnitude, 2.5, something like this. So this is very strong evolution, and that is what we would like to use with the help of today's data. Most of the time, today's data, like especially the newest one, is the gravitational waves. And as you know, we need 2 black holes to merge to produce gravitational waves. And once you have the black hole merger, you can use this tracer to halo mass with the dark matter merger. So this I will just explain in with respect to what we saw previously, that here is your black hole mass, here is your dark matter halo mass. You can parameterize this relation in a similar way to what I showed for the hydrogen and 21 centimeter. Again, crystallize it down to certain salient parameters. And this part, again, details are not super important, just that the spirit of the thing. Here is an illustration of a simulation of dark matter mergers. So when you have dark matter halos merging, people have worked out both theoretically as well as from simulations, and they have found a particular way by which you have the abundance of the merger, or the merger rate, basically. So all you have to do is you put the tracer to halo mass, which is the average relation, into the merger rate for the dark matter halo, and you will come up with the black hole merger rate, which is what is on the last last part. And the black hole merger rate again has it's like a long expression whose details are not important, but it is made up of the dark matter merger as well as the way by which the black hole populates the dark matter. And this is important because this is directly related to the James Webb and the pulsar timing data. So I will just give that connection to the data. Around about 2 years ago, they found from James Webb Space Telescope that there are a large number of dual AGNs, so-called. So dual AGN just means two active nuclei, two active black holes, ostensibly which are accreting. They are shining together. And interestingly, people always thought that the number of black holes which are to be shining together like this dual AGN was much higher than what you will expect from theory. So this is the curve which you will find, if you have a theory of the active black hole to all black holes. Whereas if you look at what was found by James Webb, it was really much higher, 0.1%. Like if you take from here to here, about 1 by 1,000 should be active, but they found that around 20-30% of their black holes were in dual AGN. Now, this is an interesting result. And how do we, use this data? So again, take this black hole to halo mass and use the merger rate, which is what is plotted here and what we saw in that same graph. We get here the merger rate of black holes as a function of their black hole mass, which is related in turn to the halo mass, as well as the redshift. And there is one more parameter called Q. This Q is just the ratio between the smaller black hole and the higher black hole. And it is something related to the analogous quantity for dark matter, which is known as zeta. And it goes from 0 to 1 basically. Now, if you take this and you look at the James Webb data, what is interesting is that you can answer a few questions. At least you can make some predictions. First is that you look at the fraction of the black hole you expect to find in merging systems. And you ask, when James Webb had found it, it was something like 20-30%. And the kind of mass, again, you can estimate that black hole mass as they had done in the James Webb Space Telescope to somewhere over here. The amount of separation also was given and what kind of Q range, etc. What is interesting is that with fiducial model, which is matched to the black hole to halo mass ratio, with that model, you get almost a similar number of black holes, all black holes in mergers, which were found by James Webb to be active, which means to be shining. Some models with, if you go to different kinds of Q, and there are some technicalities here, will find even slightly lower. So what it is telling us is that the number of all black holes in merging systems is coming out to be similar to the number of black holes which are active. Of course, correlation and causation are two different things, but definitely there is scope to say that it is likely that the merger is making the AGN shine. So all the active galactic nuclei, there will be scope for it to shine together. This is important because the shining of the AGN or the black hole, the active black hole, is an important part of its accretion and its gathering of mass and its growth. So that is something which comes out by looking at the James Webb Space Telescope data with the tracer to halo mass. What also comes out is, if you take the nanograv results, which are the pulsar timing array, which is like the gravitational waves, what you'll find is you can calculate the strain. So the strain is basically the strain is essentially what is the signal due to all of these different black holes and across a range of Q, range of Z, range of halo masses, or black hole masses essentially. And you can put the James Webb results into your model, and by then you can ask, what is the strain that you predict had it been that all the AGN are shining together? Now, if you make that assumption, of course, James Webb went to a small redshift bin, but if you assume the same across redshifts, then you actually find a big gap between what you predict as the strain, this is the red curve here, and what is the upper limit which was measured by nanograph. And that, again, interesting, because it's telling you that somewhere along the line, there is a depletion. So what is happening is that there are less black holes which are merging, or at least coming to coalescence, than you're expecting, only at the very low frequencies. And what the low frequency means is high separation. So at the largest separation, something is making them stall. There are many ideas about it in astrophysics, that what can make these things stall. But the interesting thing is, with the help of just the data from the James Webb and now from nanogram, you can sort of make a statement about it with the help of the tracer 2 halo mass. So that is basically two interesting examples of how you can use this in a multi-messenger context. Now I will come to possibly the most interesting part of it all, which is the history of the Earth and the paleoclimate. The reason why this is quite exciting, again, this is work in progress, therefore this will be a little open-ended, is that the Earth, as we know, went through a lot of extinctions in its past. And a lot of people believe that today we are on the brink of the sixth one. And what is quite interesting is, again, you can use data-driven techniques. And in the realm of geophysics, it is known as inversion theory. The same kind of what I have been describing is similarly known as inversion theory. And the context is the following. If you consider the Earth's formation 4.6 billion years ago and today, there were a lot of salient points. One of the points we know is the dinosaur extinction. It happened 65 million years ago, and it was a big one, and it's called the KT boundary, or the Cretaceous Tertiary boundary. What is not much known, as much known as dinosaur, at least in the general sense, is that the extinction, which was the worst, actually happened 200 million years before the dinosaurs, and it was called the Permian Triassic, or PTB. And this was the worst extinction event in the history of the Earth. And what the salient part is that this extinction could have been actually triggered by a greenhouse effect. So greenhouse effect, of course, we don't believe there were humans there, of course, to do that. But basically, it could have been triggered because you had a lot of volcanic eruptions, which went into what is called as flood basalt plain. And that thing was what allowed, over the course of 1 million years, the carbon dioxide levels in the atmosphere to increase. And that was the largest volcanic eruption. Such things have not happened since the dinosaur time. And this natural greenhouse effect you can model. The reason is that when you look at geological records, what is quite prominent is something called isotope anomaly. I think most of people are familiar with isotopes. These are the elements which have more different neutrons, number of neutrons compared to the standard one. So carbon has 12 or 13, like that. And this isotope anomaly happens when you have more of or less of the 13 carbon compared to 12 carbon. And one of the standard which is used for it is called a PDB, which is a fossil, which is just like a convention. It is used as a standard. This isotope anomaly is important because in physical processes, depending on temperature, you actually can get different kinds of isotope anomalies. For example, photosynthesis done in a different way makes more of these isotopes come inside the body of organisms and things like that. And therefore, most likely, and it is most sensitive to the temperature. So in high temperature, organisms absorb more of the heavy isotope, like that. So what it is called is as a paleothermometer. And why this is important is because this is how we can ask ourselves that if we compile all the carbon isotope data, if, for example, here is the way it looks like, it is always measured in per thousand, and you look at it across the Earth's history, then you can look at the amount of carbon dioxide which must be emitted into the atmosphere to match this isotope history. And this requires a little more than just physics. It needs chemistry and all that, but there are many tools which are available online, and definitely they are still being developed to do that. And that gets you this kind of result, which
Hi,
is how the temperature. Yeah.
we have 5 minutes left.
Sure, sure. I'll be done in a few minutes. So this is the temperature and like acidity, which actually match the data. So as you can see, this is the same thing. You take the data, but you are asking what kind of forcing, which means this is what is called forcing, like what kind of carbon dioxide is going into the atmosphere so that you match the data. That is the only thing that you can take away from this slide. And what we can do is when we look at the Permian Triassic, so this is work which I'm still involved in, so it is still preliminary, but basically what is quite what comes out as an average is that if you look at the age relative to the Permian Triassic, so Permian is here, and you look at 80,000 years before, the surface temperature increased. Now this is just set to 0, but the total increase was roughly about 7 degrees, 8 degrees. However, you can check the x-axis. Here, extinction took place here. We are looking 80,000 years in the past. However, the same surface temperature in today's data, what the sixth International Panel on Climate Change has found is that from 1950, it will take us only till 2100 to get the same temperature increase. And that is pretty scary, because if this average is taken, then the same thing happens for oceans as well. So you can measure what is called the pH, which is the acidity, as we know, of a liquid. And that thing, again, from before 80,000 years before extinction till now, goes down like this. And today we are doing it in 150 years. And this is something which definitely needs further work, because it's not just something to do with paleoclimate anymore. It is to do with the greenhouse effect and the climate change, which is there today. Of course, this is this is something which we need to be lend more robustness to. So I will just end by telling you that there are other proxies which we would like to use. This particular thing has been is an average trend, but we need to put uncertainties on it. Like, for example, there is another oxygen element which is useful. But as you can see, there are a lot of things we need to take care in the data. They may be correlated. Some of the errors may be underestimated, and there are gaps. So there is a lot of literature which you can look at, for example, in geostatistics and inversion theory, basically, to take care of this and help understand better the climate warming. Like, for example, even if you take climate change across many years, you may not know whether a simple power law is the right fit. And for this, you may need something more sophisticated, which is the subject of future work. So that's basically it. There are a lot of interdisciplinary things which actually have the roots in the same thing, which is data-driven astrophysics, cosmology, and geophysics. And I just want to mention that in this context, the first ever workshop in India was conducted. So I, along with the mathematics and statistics and the geophysics of Ferguson College, we were looking at how we can do something which is interdisciplinary. And this is the kind of thing which really needs data from different kinds of fields and bringing them together to sort of interconnect different approaches. So that's it. Let me just summarize by saying that there is a way by which you can look at the vast amount of neutral hydrogen in a data-driven framework to quantify both cosmology and astrophysics in cosmological forecasts, the next few experiments, including square kilometer array, as well as to look at other interpretations of molecular lines like COMAP and cross-correlate, because you want to enhance interpretation. Similarly, we can go to multi-messenger approaches, which will help us to hopefully understand the properties of black holes from the gravitational wave measurements. And this again has the roots in the same thing, which is a data-driven approach. Perhaps most excitingly, there is a way by which you can connect the Earth's paleoclimate to the carbon dioxide content using similar things, but in a geophysics context. And this is actually quite important for our current greenhouse warming and climate change. So lots of